Okay, so starting today new chapter, transistor. Okay, specifically bipolar junction transistor.
सर स्क्रीन ब्लर आ रहा है.
एक मिनट.
हाँ अभी थोड़ा ठीक है.
So bipolar junction transistor, in short we call it BJT. Okay, so why it is called bipolar? Okay, so transistor, so because it is a three-layer device. It is a three-layer device. Three-layer device. Okay, so basically a transistor is can come in two designs. One is called PNP transistor. It has a three-terminal device. On other is called your NPN transistor. These are the two designs of transistor. How you arrange the three layers. Accordingly, you can say it is a NPN or PNP transistor. If N layer is sandwiched between the two layers, two P layers, then it is a PNP transistor. Or if P layer is sandwiched between the two N layers, then it is called your NPN transistor. So it is a three-layer device. Okay, and it is called bipolar because the both majority and minority carriers participate in its operation. If you want to understand the device operation, you have to consider both the charges, minority as well as majority, that is electron and hole, both contributes. So that's why it is called bipolar junction. Okay, now why it is called transistor? So transistor का मतलब होता है, okay, there are many reasons what is we can call it transistor. Okay, the one is transistor means transfer of resistor. Transistor, okay, you can say transfer of resistance. So transfer resistance means there are two junctions in this device. Okay, two junctions, and then these two junction can be connected four ways. Okay, I can make this junction forward bias, this forward bias, this forward bias, this reverse bias, this reverse bias, this reverse bias, this reverse bias, this forward bias. So four manner I can give the biasing to these two junctions. Okay, so when I give the biasing to the junction, okay, there is a transfer of resistance. There is a one one junction will cause one junction where we are applying voltage is called input. Other junction is called your output. And when I take see the resistance value of input and output. So input is generally forward bias. Okay, your EB junction is always forward bias. Okay, we try to keep it forward bias, and for applications, for especially for amplifier application, and your CB junction, or what is CB EB I will discuss. Okay, so in basically input resistance is low and output resistance is high, and if you compare the current at input and output, both are approximately same. So resistance varying one side to other side, but current input and current output currents are almost same. That means there is a voltage gain because voltage is I into R. So there is a voltage gain, there is a transfer resistance, low resistance to high resistance. Current is moving from low resistance to high resistance. So there is a transfer resistance, there is a voltage gain, there is a power gain. That's why transistor is used as an amplifier. For understanding, let us understand this way. So this is your amplifier. It has a two terminals. You have an input, you are sending the input current, okay, and here you have output current I naught. Okay, now the value of input current and output current are almost same, but here input resistance is low. Input resistance is low. Input means input terminal, and output resistance is high. Output resistance. Let me put a resistance here. Say this is input resistance Ri. Say this is a Ro, output resistance. Output resistance is high. So current I input is almost equal to I output. But here the output voltage is high, very high compared to the input voltage, because resistance is very high. So here is we have a voltage gain. Okay. So amplifier means it will give you voltage gain, and it will give you also power gain. Okay. So this is the basic thing. Now let us understand the device structure in detail. So I told you that these are three. Yeah, we have three layers, no? So and three terminals. So one terminal is called your ammeter, other is called your base, and third is called your collector. So this is ammeter. Say this is ammeter. This is a base, and this is your collector. Okay. Now let us understand. So the first region, this is called your ammeter region. This is your ammeter region. Ammeter region. Okay. Ammeter region. This is your base region, middle part, and this is your collector region. Now ammeter region is very heavily doped. It is a heavily doped. Okay, whether it is a p type or impurity or n type impurity, this is a heavily most doping is very high. Okay, heavily doped or doping is high compared to other sections of this one. Okay, what about the property of base? Base thickness is very low. Base thickness is very less, say order of 5 micrometer. Okay, and what about the collector cross section? Okay, collector cross section is highest. Okay, collector cross section, because the collector cross section is higher. Okay, so if I talk about the doping of n region and doping of ammeter regions, let me ammeter is high compared to highest. Okay, so you can say doping of collector, doping of base. Okay, you can put in this way. Okay, you can say doping base is lowest. And if I talk about the thickness of base is lowest. Okay, say thickness of P and thickness, they can be almost same. Okay, but base thickness is lowest. Okay, so you can remember like this. Base thickness is other two thing varies. Okay, so this is a thinnest part. This is the heaviest part, heavily doped. This is the thinnest part, and this is the highest cross section. So that property you should remember, highest cross section in this design. Okay, now the most important part of this transistor is this base. Okay, so this is the special characteristics, so special design, or you can say this is the fundamental property of transistor. Okay, so because you are keeping this base very small, then only it is able to do the job which we know, the amplification. Okay, so this is the key point in the design of transistor, that this thickness is very small. Okay, because of that, injected charge carriers can move from here, this part to this part. Okay, if this become larger, then these simply, it will work simply as a two diode connected back to back. Okay, if this junction is very high, then you can say this is just like another a this is just like a two diode connection. Okay, so it will not have a much property, because current, if you are flowing current here, Here current will not come because this will be reverse bias. So because this is very thin, okay, so that's why BJT is able to perform many applications. Okay, so this is the key point in design, key design point of device, key design point, that is thinner, is very thin, and it's obviously this is highly doped. That also important. It should be highly doped. Okay, now this about a design. Okay, this exam you should remember this point: heavily doped, smallest thickness, and highest cross section. So similarly, this is here NPN transistor. Here emitter become N, base become P, this become N. Okay. Now, how these device operate, how these device work. Okay. So this device, okay, is connected in the circuit in three configurations. Okay. What are these three configuration? So three configuration. So all have a slightly different characteristics. Okay, IV characteristics. So three configuration is, one is called common base configuration. Other is called common emitter configuration. Configuration. And third is your common collector configuration. Okay. So out of three terminals, one will be grounded. Either you make base common, base grounded, either you make collector grounded or you make emitter grounded. So three will be three out of three, one will be common. Remaining with respect to this one, you will apply here forward bias or reverse bias or forward bias. So basically now your transistor has four two junctions. Okay, this is the important point. Please keep focus here. Okay, there are two things. This is EB. One is called EB junction. This is called CB junction. CB junction. Okay, so I can make this EB bus forward bias. Now, what you understand what is meaning of forward bias? P connected to the positive battery and connected to the negative battery. This is forward bias, and you can make this CB junction as reverse bias. Okay, when you do like this biasing, okay, biasing that depends on you, na, how do you want to perform this device? Okay, what is the purpose? So generally, if you want to make this is you want to amplify, so you have to make this at the low resistance. This here you have to keep it high resistance. Okay, output resistance you have to high only possible when you apply reverse bias. Okay, so operation reason, if you do give this type of biasing, the operation reason will be your active reason. Active reason means for amplification. Okay, now you say I will apply. I'll apply say both forward bias, forward bias. If you're applying both forward bias, both junction forward bias, then this is not a this is basically a saturation. Saturation means there is an this it's like just a resistance. Okay, resistance means you increase the voltage, current will increase. Okay, so current is not controlled. So output current is not controlled by input current. That is the meaning of saturation. Okay, the input output current is completely uncontrolled or uncontrolled by emitter current. They are independent of input current. Okay, so that is called saturation. So this where it is forward bias, this is basically work as a switch. Okay, switch applications. The transistor has three main applications. One is amplifier, other is second is switch. Okay, switch means if you want to make it a switch, you want to make it on, you want to make off. Okay, so when you want to make a system on, then you have to apply forward bias, forward bias. We'll discuss in detail. Okay. And then is one more is called reverse bias, reverse bias. So that is in the first junction is also reverse bias. This is also reverse bias. Reverse bias. This is called cutoff region. When this type of biasing is applied, this is called cutoff region. And last is the inverse of this one. Okay. You apply here reverse bias and you apply here forward bias. So this is nothing. This is just the inverse operation of this one. Now collector will work as a ammeter, and ammeter work with collector. But because ammeter should be heavily doped, this is not doped. So property will be get affected. You won't get good quality amplification. Whatever some property will be affected. Okay, because this is not heavy dose. You are making this ammeter. Ammeter should have more charge carriers. So this table you should remember. Okay, and most important, at least this remember this one. This one. This three. These 3 points you remember. EB junction. Okay. How I'm connecting the circuit, that doesn't matter. For amplification, EB junction should be forward bias and CB junction should be reverse bias. If EB junction forward bias, CB forward reverse bias, the operation region will be active. Okay. If both are forward bias, the operation region will be saturation, and if both are reverse bias, then the operation region will be cut off. Okay. Now let us understand, when I apply these type of biasing in common base configuration or these three configuration, so these all three configuration have a slightly different characteristics. Why? Okay. So different characteristics means different
सर
voltage. हाँ, tell me.
सर
Yes.
इसमें फोर्थ बायसिंग जो है रिवर्स बायस फॉरवर्ड, इसका एप्लीकेशन क्या है फोर्थ वाले का?
ये बोल रहा हूँ, ये इसका रिवर्स हो गया ना इसका, तो वो काम तो ऐसे
हाँ
ही
तो
करेगा।
इसका मतलब कहीं एप्लीकेबल होता है क्या?
काम तो होगा लेकिन अच्छे से काम नहीं
अच्छा,
करेगा ना।
काम ऐसे ही करेगा।
हाँ, जैसे गाड़ी है, गाड़ी को सीधे चलाओ, गाड़ी उल्टी भी चलेगी ना,
हम्म।
तो काम काम नहीं करेगा अच्छे से। ठीक है, पर
यस सर,
मूवमेंट।
यस, थैंक
Okay. So now let us understand what is common base configuration, okay, and its characteristics. For us, most important is common ammeter, because एग्जाम में सारे क्वेश्चन कॉमन एमीटर के आते हैं। ओके, अगर 1000 क्वेश्चन है तो 1000 में से 990 क्वेश्चन आपके कॉमन एमीटर के मिलेंगे, चाहे आपका एग्जाम हो चाहे कोई किसी भी इंजीनियरिंग ब्रांच का एग्जाम हो, सारे क्वेश्चन मेजरली कॉमन एमीटर पे आते हैं। हम बात करेंगे क्यों। ओके, व्हाई दैट इज इंपॉर्टेंट। सो फर्स्ट वी विल डिस्कस कॉमन बेस कॉन्फ़िगरेशन। Okay, so what do you mean by common base configuration? So the base is common, so this base is grounded basically. Okay, and before that you have to understand what is PNP and NPN transistor. Okay, if this is a PNP transistor and this is a common base, okay, so this is your base, this is your, say, ammeter, this is a collector. So this is suppose this is a PNP. So this part is PNP. So this symbol will be like this. This for PNP transistor. Current direction will be always from P to N. So because PNP transistor, this is the P, this is the N, base is N. So current direction will put like this. This is the PNP. Okay. Similarly, if you want to make a NPN transistor, okay. So this will be your E. This will be your base. This will be a collector. Okay. Now NPN or NPN. So current will be from P to N. This is your NPN transistor. NPN transistor. Okay. So that difference you should understand. So I'm discussing here PNP transistor. You can take NPN transistor also. Okay. Now here common base. So this is the E junction, is a B junction. I have to make this junction forward bias, and this is a BCB junction. I want to make it a reverse bias. So this is the PN junction diode. This is the NP junction diode. Okay. So if I want to make it forward bias, if I want to work as a amplifier, so I have to make this. So this is base, okay. So I am keeping this as a battery VB, okay. So I'm connecting P to positive, and this is ground because I have to make this forward bias. Similarly, this is my collector. I have to want to make it reverse bias. So I'll connect a variable battery, okay, and this is my VCC because I'm applying the collector, okay. So this is the basically your device. You want to make a forward bias, you apply like this. You apply reverse bias like this, okay. So basically you're applying here voltage, input voltage, and here you're taking the output voltage, okay. So this is VCB. So this is basically your voltage drop is VBE, and from here to here the voltage drop is VCB, okay. VB with respect to B, so VBE positive, so you write VBE, you can write VEB also, and the VBE plus VCB, this the voltage between V and C is called VCE or VEC, whatever you want to measure, difference of voltage, okay. And in the circuit you have to always remember this VCE junction, the drop here junction, this drop plus this drop is equal. So this VC is basically your VBE plus VCB. And what is the value of VBE? What is the cutoff voltage for VBE? Tell me. What is the cutoff voltage for diode?
0.7 volt for silicon.
Silicon. So if it is a silicon diode, you can say VCE will be equal to 0.7 volt plus VCB, okay, for silicon. And if you have a germanium, this equation will read like this: 0.3 VCB, okay, VCB for germanium. You can also read this equation like this, okay. So this VB is always fixed, okay. Almost fixed means it is very slightly around 0.7, say 0.655 to 0.65 or 0.5 to 0.7. Very slight variation is there. So for application purpose, when we are solving the circuit, we have to take some constant value. So this VBE is always constant. Very slightly variation is there, okay. So circuit will take constant, but drawing IV characteristics I will vary little bit, okay. And this is your VCB. So when you're changing the VCC, basically the voltage drop is happening here. So you are applying VCB here. Okay. Now let us understand what happens, how the device operate and how we draw the IV characteristics. So this is the P junction. Here you have a holes, high concentration of holes. Okay, so this is the P part. You have so many holes here. Majority charge carriers are hole. And what you're doing, you're applying a positive battery forward bias. That means you're pushing these holes, okay. Exact operation, you are pulling the electrons. So the pulling the electron is the same like a repelling the holes. So when you're applying forward bias, these hole get injected, okay. Why inject? How injection happens? Do diffusion, okay. So there is a junction, there is a barrier. As you apply forward bias, this barrier width will decrease, and I told you whenever barrier width decreases, that means you are opening the gate, okay. In the equilibrium the gate is closed, okay. And why it is closed we have discussed in equilibrium PN junction. But now you're applying forward bias, that means you are getting the barrier down or you're slightly opening the gain. So again the diffusion will take place and these holes will go reach in the base region, okay. Say base, these holes are coming in base region. Now this base is very thin and very lightly doped. So these holes cannot be recombined with the electron because this is n doping, and doping is very small. So we don't get any loss, very slightly loss of holes, okay. So what will happen? And here, because the base is thin and you're applying high voltage here, VCB at collector is applied here. We're applying what? P and P. Reverse this is a negative battery. That means it's pulling the holes. Okay. You can understand the reverse magnets for the electron, but you can understand, suppose these holes are moving and this is very thin, and no holes are recombining, very little holes are recombining, so this whole current will reach here. Okay, so here a current will flow called IE will go here, and out of IV 99% or 98% electron will reach here, and they will combine and they'll form a current called IC here. Okay, so basically what is happening when you're applying ammeter, so a current I is flowing here. Okay, IC is going down. Now because some of the hole get recombined here, that means what? Holes are reducing. Holes are reducing means you have to uh, should come from somewhere. Okay, so what will happen? This These holes are reducing, that means electrons are increasing. So what will happen now? These holes will come from this terminal. You can understand this way. So the direction of IB will be here because your holes are decreasing. So this conservation, this hole will come here. So now IE, no, here electrons are reducing because this is N na. So because of this N part, so these holes are combining with this sum of this electron. So the electron is reducing. So electrons are reducing or increasing. Just 1 minute. Electrons are reducing. So these electron should come from here. Okay. So electron movement is here. That means your IB should go down. Your IB should go down. Okay. So basically your I should be equal to IC plus IB. That point you have to remember. Okay. So basically what is happening? Ah,
So position of current in IP is same for also for the case of NPN.
yeah, direction will be different. Directions will be different. Okay. So ammeter I is flowing here, IP going out, and IB is coming down. In the case of NPN, what will happen? This IB will go here, IC go inside, and IB also go inside because IB plus IC should make IE. Okay. So now what is happening here? You have this device. Okay. A current IE is coming here, a current IC, okay, from a meter, and is a collector, a IC current flowing here, okay, and a IB current is a base, a IB current is flowing here, okay. So why these three phenomena is happening? Okay, why? Because here is a forward bias, here is the reverse bias. Forward bias is injecting the charge carriers, reverse bias is capturing. Okay. So one more thing is happening here. Tell me. Here is forward bias, but here is also reverse bias. Okay.
Yes,
So what will happen because of this reverse bias? What will happen? So here this is the NP. So I am applying minus here, plus here, plus here. So this is a reverse bias. I am applying VCB here to this junction. So what will happen? In reverse bias, also a current flows from where? Current flows from positive. This side. This current is called what?
leakage current.
Leakage current, IC saturation. Okay. Leakage current or saturation current, reverse saturation current. This is called reverse saturation current. So when I'm applying this junction, I'm making also reverse bias. So one more current is flowing, that is called ICBO. ICBO matlab this current is going like this. This current is called ICBO. Okay. Reverse saturation current or leakage current. Reverse saturation current. Okay. In BO means common emitter mode, common such current, common base mode, common base configuration, common base configuration. Okay, ICO, common base configuration. Reverse saturation current in common base configuration. Okay.
सर
Yes, tell me.
सर आईसीबीओ की डायरेक्शन क्या होगी सर
यहाँ
डायग्राम में?
इसमें बताओ ना क्या होगी? इस टर्मिनल से इस टर्मिनल पे, इस टर्मिनल से इस टर्मिनल पे. Okay. Circuit क्या है?
Yes, sir.
This circuit is there. This is the direction of ICBO. Okay.
Okay. Yes.
Now let us write the fundamental current equation for transistor. Okay. So we'll come back to this. So basically now IE is equal to what? IE is equal to your IC. Okay. This IC plus IB. Yes or no? Tell me. Can I write like this? Or should I, or I have to write IC first? IC, IC, let me write first IC. Okay. So IC. Okay. So what is IC? So IC is made of two currents. Okay. 99%, 90% very high amount of this one reaching here. That means my IC is almost equal to alpha IE. Okay. Alpha is what? Current gain coefficient. Current gain. Okay. So IC is made of IE, that is alpha of IE, and plus this is ICBO, and this is your ICBO. Okay. So this is the equation number 1. So I'm writing the fundamental equations for transistor. Fundamental equations for transistor. Okay. Now what is other thing? What I can write? I can write IB. IB is coming from IB is coming from which current? Is IE alpha
IE and
IE
IC.
out of IB alpha IE comes here. Remaining will go here. How much? 1 minus alpha IE. Yes or no? The total current is IE. Out of IE alpha E gone here. Remaining 1 minus I minus alpha IE will go down. So my IB is equal to 1 minus alpha IE minus, because IB is down, ICBO. This is my equation number 2. Okay. Now you just add these two equation. Just add this equation 1 or 2. So my IC plus IB, these two will cancel out. Alpha I cancel out. This will remain IE. So this is the main equation of transistor. IC plus IB should be equal to IE.
सर एक बार सेकंड इक्वेशन बता दीजिए.
Second equation, IB is coming. This is the total current. 0.99 IE goes here. Alpha IE goes here. Okay. 1 minus alpha IE goes down. Okay. So IB is made of what? IB is this 1 minus alpha IE, and this ICBO is reverse. So I am putting minus here. Clear?
Yes sir.
Okay. So let us now, this is the current. Okay. Now what we have to discuss? We have to discuss about this alpha. Okay. Now I have to discuss the IB character. This is the current equation valid for all 3 configurations. There will be slightly change we'll do. So this is for common base configuration. Okay. Now we'll go in the IV characteristics of this common base configuration. The mechanism, you understand what is happening. Okay. Now one more thing I want to discuss here is alpha. Okay. So alpha value is what? Alpha value is basically, tell me, alpha value is IC minus ICBO upon IE. Okay. And you know that this is the exact value of alpha. Exact value of alpha. But ICBO is microampere, this is a milliampere. So generally we write approximately this. I neglect, I write IC upon IE. Okay. And this is what? This is the current gain. Current gain. Actually, it's not current gain. Current is slightly reducing, almost equal. The ratio is almost equal to 1. Okay. Generally 0.82, 0.82, 0.99. They're depending on the question and design the circuit could be given. So this is the current gain in common base configuration. Common base configuration. So that means you have to remember current is almost same. Input and output currents are almost same in this configuration because alpha is close to 1. Alpha is close to 1. That says IE input current and output current IC both are same in this configuration. Okay. So what is the advantage? Okay. You are putting some current. It's like a giving a it's like just a you give some current, same current you're getting. So, but how what is the advantage? You'll see that one now. So this is this is the current gain. Okay. This is the current gain, this configuration. Now let me slightly change this circuit and draw in normal way. Okay. So this generally we use this one so you understand better because exam में तो circuit ऐसे ही बनाएगा ना. So this is your base, this is your ammeter. Okay, this is your collector, this is your base, and circuit is same. I am applying here PNP. So I'll take now. So let us take PNP only. Okay, so this is PNP, PNP. Okay, so this is what? This is your PNP. So I want positive here. Okay, this is grounded, and this is PNP. Collector is here. I want reverse bias. So this is a reverse bias. Okay, this is your VBB, and this is your VCC. I'm applying here. This is your PNP transistor. Okay, now you understand current IE is going here, IE is going here, IC is coming out, IB is coming out. Okay, ICBO going inside, ICBO getting add with this one, but ICBO generally we neglect. Okay, because this is very less. ICBO. Now input output characteristics of common base configuration. Input, first discuss input characteristics. So input characteristics means the relation between, okay, relation between input and output, input current and input voltage. Okay, so relation between IE and VBE. Okay, keeping output voltage VCB constant. Okay, so here when you're applying the voltage drop across the diode, this junction is VBE. Okay, and you're varying this VBE, so this current will vary. Don't see this one. You're applying something, there may be some resistance also there. But when you're applying this one here, this is like looking like a parallel, but don't understand. You see, you're applying something here, varying here, and some voltage is varying here. You are interested in this one. This is not in this battery. Okay, here some resistance, maybe some drop may be there. How much voltage is getting drop at the junction? That is your main thing, VBE. So here voltage drop is VBE, and you are drawing current IE, keeping this this VCB, because if you change supply some VCC, here some VCB will also come. Keeping this VCB constant, plot this one called your input characteristics. Let us draw this input characteristics. So this input characteristics will come like this: IE versus VBE, and because this is a diode only, input output current of junction, so this will come like this only, keeping VCB constant. Okay, and this value will be slightly 0. Vary 0.627, but for circuits application we have to take constant, but it is slightly varying. Okay, this is cutoff and slightly varying, and here it is becoming constant. So this is your VCB, and exactly practical, even this comes like this. Okay, say like this. Okay, it's slightly changing and keeping VCB constant. Say VCB is 5 volt. I'm keeping VCB 5 volt, and I'm getting IE current here. My current IE. So this is IV characteristics, and I can find the input resistance. Okay, and the input resistance values come to order. I think the input value resistance order is around 25 ohm. Okay, here input resistance R input, okay, in common base configuration, how much will come? Delta IE upon delta VCB, delta VB, so delta VB upon delta IE, delta VB upon delta IE, keeping VCB constant. Okay, and this value is very low, around 25 ohm. Okay, so now let us what happen if I change the VCB, if I increase the VCB 5 to 10 volt, that means I increase the reverse bias here. So that means if I make this point more positive compared to this one, okay, P and P, no, more negative compared to this one. If I make this is negative is there, if I apply VCB, this become more negative. So with respect to this become what? More positive? Yes or no? Automatically, if say here some voltage there, okay, and I'm applying some voltage here, I'm changing this VE, so my VCB increases, so this become more negative P part compared to, so this is a VC, this is a VC, so VC is what? Basically what your VCE is, your equal to VBE plus VCB. Okay, that means I'm keeping this constant, same volt, same. I'm not touching this one. If I'm increasing the VCB, this VCB, so what will happen? This will increase. Okay. Now, if I want to make this constant, what should I do? This I have always increased, so I have to reduce this one. Yes or no? Say with this VC is VCB. Now I have increased this VCB, and I kept this constant to VC increase. But I want the situation should be same. Current should come same, outer current. Okay. So I'll have to reduce VCE, or I have to reduce this one, or I have to reduce this one. So sum should come same. Okay. So why I'm trying to say here, whenever you apply, you increase the VCB here. Okay, you have to decrease VB to remain this same current. Okay, on an other manner, what I'm trying to say, that whenever you increase the VCB, there is a junction. This junction is called P and P. Okay, if you make this junction reverse bias, the depletion layer width will increase. Yeah, this depletion layer width will increase, so your base become thinner. Okay, so base become thinner means what will happen? Now you require less VBE to attain the same IE, because the width become resistance become decreased. Now earlier the junction was like this big, so you're applying some voltage 0.7. Now because the width become decreased, you require less voltage to attain the same amount of current IE. Okay, or in other manner you can say, when I increase the VCB here, I am putting more negative here, so it will effectively pull the holes. That means collecting power is increasing. Obviously, reverse bias is what? Collecting power. Water is injecting our input. You are collecting those all the things using this battery. So you're capturing this efficiency. That means your IC is increasing. IC is increasing means what? Your IE is increasing. Okay. That means you get if you increase the VCB, your IE will increase. IE will increase if you increase the VCB equal to 10 volt. Okay, and so here this is the value. That means the current what you are getting earlier for higher VBE, that same current you will get now for lower VBE. So your VBE will slightly decrease if you want to keep the current same. That's the point. That's not important point. Okay, but just to show, you have to only remember that this is fixed. okay, or slightly varying. So if you are applying VCB increasing, so if you want to get same current, this one, you have to slightly reduce this VAB, because now you have less voltage required, because this power is increasing. Okay, suppose you want this is giving some push of 10 Newton, and you are giving some push of pull of 10 Newton. You require total 15 Newton to get same the thing to move. Now if you increase this 15 Newton, you require here only 5 Newton force. Okay, so still the sum is 20. That means if you want the same current here, if you increase same current here, if you're increasing this VCB, you have to reduce this VB. That is the point. Okay, you have to remember. And why it is happening? Which is happening because the base width modulation. Base width modulation का मतलब क्या है? Base width modulation. Base width modulation. Modulation means increasing VCB or reverse bias. Increasing VCB decreases base width. Okay, base width decreases. Okay, and minority concentration gradient increases. Okay, that we'll discuss later sometime, but only for the moment you have to remain this point. Okay, so this is the input characteristics. That is not important. Only you remember the value is 25 ohm, and voltage is your 0.7, around 0.7 volt. Okay, this nearby 0.7. This thing you have to remember. Input characteristics is not important for the transistor. Now output characteristics is important. To put the heading output characteristics. So output
सर वो
characteristic.
बेस वेट मॉड्यूलेशन के नीचे क्या लिखा हुआ था, वो नोट नहीं हुआ था।
Base with modulation मतलब increasing VCB, the width of base region will decrease. Okay, again I'm repeating, increasing the VCB, the width of base region will decrease because depletion layer बढ़ेगा, so base width will decrease. Okay, and if base width decreases, there will be less recombination. Okay, I'm writing again here. What is the meaning of base width modulation? Base, अब एग्जाम के लिए ये खाली बस याद रखने वाले पॉइंट है कि छोटा सा क्वेश्चन आ गया तो सर्किट के लिए इतनी ज्यादा इंपॉर्टेंट। बेस विथ मॉड्यूलेशन इज व्हाट? बेस विथ मॉड्यूलेशन मींस if you increase the VCB, okay, base width decreases, base width decreases, okay, increasing. If this increases, base width decreases, that means recombination decreases. Recombination of holes or electron what are coming from injected, recombination decreases. Okay, decreases. किसका recombination? Injected carriers का. Injected carrier recombination decreases. If recombination decreasing, that means automatically what comes? IB goes down. IB decreases. IB decreases. IE. IB, sorry, IB. I here. So IB decreases here. Okay. That means more IE reaching here, Okay. That means collection is more. That okay. Whatever way you want to understand, that you have to understand. So that means applying voltage here, reverse bias means applying forward bias here. That you have to understand. If this become more negative, automatically this become more positive. So it will give now more current. Okay. So if you want to same current, you have to reduce this VB. That difference I told you by the force of Newton push. You understand that way. VB plus VC, VVC is equal to VC. Okay. So now the output characteristics. So output characteristic is what? Output characteristic means the relation between output current. So what is output current here? Output current is what? Okay. Like there was an input current. Input current was IE in common base. Okay. Input voltage was what? VB, okay, and output voltage was VCB, okay. Now for output characteristics, okay, your output current is your IC, okay. Output voltage here is your VCB, and input current for this configuration is IE, okay. So now how to draw IV characteristics, keeping the relation between IC versus VCB, keeping IE constant. This is called output characteristics, okay. Why we are drawing output characteristics? Because we want to know how much resistance is coming at output side. Input side is very low, okay, because that is the only application of amplifier. So we have to see how much resistance is coming this side. So we have to experimentally measure, okay. So now let me draw again the, if you note down, then I will plot here because I require this circuit here. Okay, shall I erase this one?
Yes, sir.
Now I am plotting this curve IC versus VCB, okay. And I told you that this has to be negative, okay. So VBC, so I'm plotting this positive, okay, no issue, okay. So how the characteristics comes if I draw this one. Just give me 1 minute. That I have left something here. No. Common base, okay. Now common base configuration. So I'm plotting this curve like this. IC, okay. This is a negative VCB, okay. This is a positive scale. This is a negative scale. So if this VCB become negative, then what is the situation? So if you want to make a active region, if active region, you want to amplify, here should be resistance high, this should be negative. This should be positive. This should be what? Positive, actually positive, but I'm plotting this opposite, okay. So here this is a negative value, okay. But I'm, instead of say VCB, VBC, this VCB, or you type VBC, the same thing. You would understand here. So let me everything change now. So this is my NPN transistor, okay, because I'm drawing for NPN transistor now. NPN transistor, okay. So NPN transistor, everything becomes opposite. This IC goes inside, IE also goes outside, and say this IB also goes inside, okay. This is the main currents I'm drawing now. NPN, so NPN, okay. So current will, tell me current, what is the current direction? Tell me for NPN transistor. Current direction will be like this, NPN transistor. So I am drawing this for NPN transistor. So for NPN transistor, I have to change the polarities. I have to make this positive, okay. This is VCC. So now VCP become positive, okay, and here I have to make negative. So this is my VBV, okay. Because I am plotting for NPN transistor, because NPN transistor ही हमारे काम आएगा बार बार, तो फिर दोबारा दो दफा करना पड़ेगा, okay. So this is NPN transistor, okay. So I want positive voltage here, negative voltage here, okay, for forward bias and reverse bias. If I make this VCB also negative, then this will also become forward bias, this will also become forward bias. That we don't want, okay. So when I make both the thing. If I change now BCB and note down the IC, if I apply negative VC, my current my graph goes like this. My graph goes like this. We'll discuss what is this one. So this is my IC. So basically what I'm measuring, I am measuring the IC, keeping IE constant. Okay, keeping IE constant. So these are IE values. This is IE values. IE values, IE values, IE values, IE values. Okay. So can I make this IE 0? How can I make IE 0? Tell me. अगर मुझे इस IE को 0 करना है तो कैसे 0 करूंगा? इंजेक्शन करंट को. If I want to make IE 0, what should I do? Tell me. IE is a forward bias current in this region, junction. If I want to make 0, what should I do? Usual. अगर IE को 0 करना है तो क्या करना पड़ेगा?
सर अगर इक्वेशन से जाएं तो IB इक्वल टू IC करना होगा.
अरे भैया यार you remember this input curve ना? This is your IE. This is your VB.
Yes, sir.
If I want to make this current 0, my VB should be less than 0.7. Yes or no?
Yes, sir. Yes, sir.
Okay. If
कट
I
ऑफ से
make
कम होना चाहिए.
cut off से कम होना चाहिए. If I make this VBB, this somehow this reduces voltage and my VB goes down 0.7, automatically current becomes 0. Either you remove this battery, so my VB becomes 0. Okay. VB, this voltage becomes 0, so automatically current becomes 0. Okay. So if this battery is not there, here whether some current will flow or no? Here, tell me. In this circuit, any current will flow or no?
ICBO.
Yes,
No,
very
sir.
good. ICBO reverse saturation current तो flow करेगा ना? If IE finished, IC finished. Okay. Because IC is come from IE only. But ICBO is coming in reverse saturation current. This ये circuit अभी जिंदा है ना? Okay.
Yes, sir.
And PN. तो ये सर्किट अभी जिंदा है. That means this is minus, this is plus. Okay. So here also you're applying VCC. So some VCB is coming here and a reverse saturation current is flowing. Okay. So if I keep IE 0, okay, my IC will be equal to ICBO. So this point will be equal to IC. So IC will be ICBO. So this point is equal to ICBO. So this ICBO current will flow for this value of IE. And to make IE 0, if you want to make IE 0, you have to reduce VB VB should be less than 0.7 volt. Okay. If VB is less than 0.7, automatically IE will become 0 and the circuit in the current only ICBO will be flowing. Okay. Now say second measurement. I am keeping I1 1 milliampere. Okay. And I am coming from here. Negative का मतलब क्या है? Saturation. Now I'm coming positive VCB. So I am getting some IC value. So IE 1 milliampere. What will the value of IC tell me? What is the value of IC? If IE is 1 milliampere, what is the value of IC? श्योर पढ़ने का?
IC equal to IB means IC equal to IE. So
IC equal to IE because IB is only small microampere. IE is equal to IC plus IB. So here this will be also 1 milliampere. This will be also 2 if I say this is 2 milliampere, so here also 2 milliampere current come. If you say 3 milliampere, this is this type of drivers you have drawn in your laboratory na classroom, MSc or BSc.
Yes, sir.
So why are you forgetting this 3 milliampere? If it is a 4 milliampere, then this will be also 4 milliampere. This is 5 milliampere. This will be also 5 milliampere. Almost same current will flow. But if you're applying this VCB negative, if you keep on increasing, you're applying positive. If you apply negative, then this will repel. Okay. Now you're applying reverse bias. This plus is collecting whatever electrons are coming from here n side. Holes are moving like this. Electrons are coming from n, injecting here, and we are collecting. But if we make this as a forward bias, this also positive. So that means it is a whatever injected charge is coming that we are repelling. So slowly, when you apply negative, this current will drop to 0. Okay. If you make this one positive, then there will be no IC will be flowing. IC will go to 0. Okay. So this is output characteristics for this common base configuration. Now, what is the important thing for us to remember here? I told you the input resistance. Now I'm into output resistance. Output resistance RO. Output resistance RO. So output resistance is basically what? Tell me, delta VCB upon delta IC. Okay. What is the value of delta IC here? Tell me for each curve. What is the value of delta IC? For this curve, what is the value of delta IC? Almost 0. When I'm increasing VCB, I'm changing VCB, my IC is almost constant. Okay. So this IC is not changing. It's a constant almost. So this ideally should be infinite. That's why the curve is like this. Curve is straight line. I versus V curve is a straight line. And this is what? This is for what? This is for the thing which has a infinite resistance. Okay. If I draw this same curve like this, say this is my V, this is my I. So this slope will be what? Slope will be like this. Okay. And this is how much slope. Resistance means what? Slope V by I. V by I is tan theta 90. Tan 90 is what? Infinite. That means this type of characteristic shows infinite output resistance. Input resistance is very low, output resistance is very high. Okay, that is the transfer of resistance. Okay, so ideally this should be ideally. Okay, but practically it's not infinite. Practically it will be in mega ohm. Okay, so for safe point you can write is say R0 for practical condition is around 500 kilo ohm. Okay, or you can put limit also. What is the issue? 500 kilo ohm to 1 mega ohm. This is the output resistance. Okay, so this device has low resistance. This common base configuration, low input resistance, high output resistance. Okay, current gain, you're not getting your input current and output current almost same. So current gain is less than 1, 0.99, you can assume. Okay, so if current gain is not there but resistance gain is there, so automatically this has some voltage gain. Okay, and power gain. That's why this device can work as an amplifier. Now we have to understand the three regions properly. Okay, three regions. So this is called, this parallel graph, this region is called active. This is called active. Okay, active means what? Active means EB junction forward bias, collector CB junction reverse bias. BCB should be reverse bias. So this BCB positive is a reverse bias. So when this is positive, okay, and this junction is positive, what is the signature of this? How to know this junction is positive? Because IE is flowing. So if IE is flowing, you're getting some IE value, IE is flowing, and you're applying this VCB, that means VB is positive, VCB is positive, VB is negative, VCB is positive. So this region is called active region. Okay. And opposite to this one, where VCB negative and input also negative because current is varying. This region is called saturation region. This region is called saturation region. Okay. And when you are making this I0, that means basically you are making this as a reverse bias. Okay, when you're removing this battery and you're putting IE0, that is basically reverse bias. So the region below IE0 is called your cutoff region. This is your cutoff region. Okay. So whenever you want to want transistor to work in saturation region, you apply this is forward bias, this is forward bias. Okay. For NPN transistor, negative. NPN transistor, this should be negative. Forward bias give you this kind of curve, saturation. Okay. So here your IC is independent of IE. Okay. Your IE is varying like this. With changing voltage, your IC is varying like this. Okay. What is the value of IE? It doesn't depend. Okay. Transistor is a basically current control device. So here no control current. So this region is called this negative region. This negative region. Okay. This is called your saturation region. This the region above this one where I is flowing. This is active region. In I0, when you're making this also reverse bias. This is also reverse bias. Then this region is called cutoff region. Okay. Tell me whether you understood this three region. Yes or no?
Yes, sir.
Okay. So if I change the PNP transistor, the sign of the voltages will be changed. Okay. So you should know by seeing the sign whether it is a forward bias, which junction is forward bias and which junction is reverse bias, and by seeing the sign and magnitude, you can identify whether your transistor is in cutoff region or your transistor is in forward region or transistor is saturation region. Because by knowing the voltage and current value and their polarity, you decide what is the operation region, and that type of questions come in exam. Okay, so this was your common ammeter configuration. Now next is just I'll take 1 minute break and we'll do common ammeter configuration. Okay. Okay. So let us now discuss your common ammeter configuration, which is most useful for us. Just now we have written the current equation. Current equations were what? You want IC, that is your alpha IE plus ICB. Okay. Your IB was 1 minus alpha IE minus ICBO, and of course your IE was IC plus IB. These were three equations. Okay. Now these equations will slightly change. Okay. Now what is common ammeter configuration? So common ammeter configuration. This is common ammeter configuration. This is ammeter. This is the base, and this is the collector. Okay. Now you are applying. So now your input current is your IB. So now if I say NPN transistors, NPN, so current will be always ammeter side. So and ammeter is grounded now. So ammeter is grounded. Okay. here I'm applying, say, voltage again, VCC, and here again I'm applying this E is there, so I'll put E. So NP, I want forward bias here, forward bias, and so this should be plus, this should be minus. Okay. Now let me discuss this one and say this is VEE. And again, this is VBE. VB is positive, VEB negative. Okay. And here you're applying, now this is VCE. VCE. Okay. Now input and output change. Okay. Now input is your this one, base emitter, and output is your collector emitter. But that should not change our original definition. I have to make EB junction forward bias and CB junction reverse bias. So now this is NPN, NPN, this is a plus. So I'm making N negative. I'm applying VCE, which is positive, and this VCE positive. This means VCE is always equal to VBE plus VCB. That means VCB is positive, and VCB is positive means what? N is what? Positive. This is what? Positive. The VCB. The VC is positive. This is positive. Automatically, this is positive. That means I'm applying, still I'm applying reverse bias on the collector base junction. But output I'm taking like this. That is only difference. Okay. Junction, our two main junction that you have to always keep in mind. Emitter base junction will be forward bias. So this is emitter base junction forward bias. Okay. Collector base junction, this should be reverse bias. And to make this reverse bias, this N should be positive because this is the NPN transistor. So I am putting positive here. This still your this is there. Now only, so now here current is IB, input current is IB, and output current is what? Output current say IC. Okay, this is my transistor. So here IC current is flowing, and so NPN में direction क्या था? What was the direction? Tell me in NPN transistor. NPN transistor current is going down.
सर ऊपर की साइड
ऊपर का जा रहा था, आई तो बाहर निकल रहा था. NPN इलेक्ट्रॉन को पुश कर रहा है अंदर, करंट आ रही है बाहर. ओके, सो करंट आ रही है बाहर, IC is going inside. Okay, and IB also going inside. So IC and IB combining giving you IE. This is your okay. So here input current is IB, output current is high IC, so gain is very high. Okay, so what I'll write here, this is my IC. Okay, this alpha I can write, this is the IC plus IB plus ICBO, this equation. Okay, and this gives me what? This gives me IC equals to what? IC here, IC alpha IC minus alpha IC. Okay, minus alpha IC is 1 minus alpha IB plus ICBO. Okay, alpha IB, and I'm sending this IC alpha here. So I get IC equals to alpha upon 1 minus alpha IB plus ICBO upon 1 minus alpha. So this IC become this become alpha 1 minus is a beta current gain in common emitter configuration beta IB, and this become ICEO reverse saturation current in common emitter configuration. This equation slightly modifies. Okay, and beta is what? Beta is basically IC minus ICO upon IB. Okay, exact relation is this one. You should know this one, and a rough relation you can neglect this one, and you should write I beta equal to ICIB. Okay, again, now only we are interested in input and output characteristics. Okay, so we'll draw now input and output characteristics. So shall I erase this one?
Yes, sir.
So input characteristics. Input characteristics. Input characteristics means what is input current here? Input current. Common ammeter I'm doing common. Input current is IB. Input voltage is again input voltage is again VB, and the output voltage is what? VCE. Okay. Now let us discuss the graph. So input graph will be input characteristic means IB versus VB graph, keeping VC constant. Okay, constant. And this graph has same nature because you are making base emitter junction. So input current will be IB this time. This will be your VB, and graph will come here. Keep VC constant. VC is a 5 volt. But here now it's slightly changed. Okay. Now what happens if I increase the VCE to 10 volt? क्या होगा? If you increase the VCE, say 10 volt, graph will come like this. Now it will not go this side, it will come this side. VC 10 volt, okay? Because again, what will happen if you are increasing VCE, okay? VC increasing means your VC, this is VCB, and this is your VB, okay? If you are increasing VCE, your VCB also increasing, and whenever VCB increases, base width reduces, base width will get reduced, and whenever base width reduce, your IB decreases, okay? And now if you want to get the same IB, okay, so you have to increase this VP. That's why the VP, the current what you're getting here, if you want to get same current, same current at different VCE, you have to apply high VPE. Okay, so that is the reason this curve comes like this. I hope it is clear to you. It's clear? Tell me.
Yes, sir.
Okay. So you have to keeping this IB constant. Okay, for keeping IB constant, you have to increase the VP. I am writing for keeping IB constant. VB has to increase. Okay, reason is clear because now you want more IB, you have more voltage input. Want more IB, you have more voltage. It's a simple things. Only you have to give some attention. Okay, now values will change. Input resistance values in generally for this case, okay, slightly higher. So input resistance value is 1 kilo ohm. Okay, input resistance in common ammeter case it is slightly higher. Okay, 1 kilo well 1 kilo. That is not a good thing. Okay, because we are always input resistance low, but still this configuration has a several advantages over other configurations. Now, for example, if I want to draw output characteristics, and is the most important characteristics for our transistor. सारे question or every problem will be done by this curve. Okay, Let us understand. So same thing. Now you can here you plot IC. You have to apply VC. Okay. So if VC is 0, if VC is 0, that means what? Your VB plus VCB, everything becomes 0. Okay. So now the curve will start from like this. So output characteristics means keeping input current constant. Input current is, that means, so this output current is IC. Output current is IC. Output voltage is VC. So I am taking so much time for this one because this is the only thing you have to understand in transistor, nothing else. Okay. After that, the rest of the thing is just a cakewalk. So you have to be confident about these characteristics. That's why I am repeating and taking so much time. So this is output current IC, output voltage is VCE. Okay. Input current is your IB. Okay. So the output characteristic means IC versus VC curve, keeping IB constant. Okay. Now say beta is, say, 100. For this common limit, say beta will be 100. Now my IB is 0. If IB is 0, what is the value of IC? Tell me. What is the value of IC? What is the value of IC? If IB is 0. How can you
IC,
ICEO? Very good. This so only ICEO will flow. Leakage current will flow. IB you can make 0 only making VB is 0. So once you made the VB 0 in the input, IB becomes 0. So that junction become reverse bias. Either 0 you make negative, that input become reverse bias, and output is already reverse bias because you're applying VC positive, NPN transistor. N means negative, VC positive. So this is already reverse bias. So this region become cutoff region like previous year. Okay. Now VC cannot go negative. Okay, VC cannot go negative. So VC has to be like this only. Now if you say IB is equal to say 10 microampere, what is the value of IC? Tell me. If IB is 110 microampere, 10 microampere, what is the value of IC? IC is equal to what? IC is equal to beta IB, current gain. So beta values, I'm telling you 100. This graph I'm putting for 100 value. So if IB is 10, beta is 100,000 microampere, this become 1 milliampere. Okay. So this graph is slightly tilted. Okay. And if I say this is my IB equals to 20 microampere, then this become 2 milliampere. If I say this is my 30 microampere, and this become 3 milliampere. If you say this is my 40 microampere, so this become my 4 milliampere. This is my curve, and this is slightly tilted. Okay, this is not here. So tilted curve shows this is not infinite, but it's still very high. Okay, not infinite. Now let us discuss this curve. This is only most important curve. This should be slightly like this. No issue. This should be slightly more like this. Understanding. I am a little tilted more. You can make it here. Now, what is the important in this curve to understand? We want to understand this curve. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . active region VC, for VC is to be active, okay, this minimum value should be 0.7 volt. Okay, whatever silicon value is given, because your VC is VB plus VCB. Okay, VCB. Now say my VC become less than, suppose VCB is become 0.6, VB become what? VB is 0.7. So what is the value of VCB? VCB become negative 0.1 volt. Okay. And for NPN transistor, if you want to be NPN transistor, if you want to be in the active region, your VCB should be positive.
Yes.
Positive. So that means if you're in the circuit, if VC is going less than 0.7 volt, that will be saturation region. Okay, if VC goes to 0, nearby 0, so that is the indication, or you always check in the circuit if VC is close to 0, okay, that means for here 0 here like this, so current will be very high. I am plotting this curve again, so you should understand this curve is just like this. Okay, so this curve is just like very close to here IC. So if VC is 0, that is the VC curve. VC is close to 0, the current in the circuit will flow IC will be equal to IC saturation. Very high current will flow in the circuit. Saturation current will flow. Okay. So if this happens, that is called saturation region. Transistor is working in a saturation region. Okay. But VC is somewhere here positive. If VC is 0 or VC negative, negative never can comes. Okay. But just to understand, if VC goes here or very close to 0, then this is the saturation region. If it is far, it's a 2 volt, 3 volt, 4 volt, 5 volt, okay, much larger than VB, then this makes this short, the VCB also positive, NPN transistor reverse bias, and of course the current is flowing, IB is flowing, the lattice junction is forward bias, this junction is reverse bias. This region is called active region again. So this region is active region. Okay, this is active region, and this is saturation. This part is saturation region, and this part under is cutoff region. Okay, so now finally in the summary, you don't need to remember everything. You just have to remember that your VB should be greater than 0.7 if you want to make your junction forward bias, EP junction forward bias. Okay, and VC also should be greater than 0.7. Okay, because VC ultimately makes VCB plus VCE. So your VC should be close to 1 volt. Roughly you can remember. If your VP less than 0.7 volt, the DP junction will become reverse bias. If your VC less than 0.7 or close to 0, then your this junction also become reverse bias. Your transistor is in cutoff. That is a signature. You should find the values of this one in the circuit. If these values are close to 0, cutoff. Okay. If VB is not, VB is greater than VB is 0.7 or greater than 0.7, that means IB is, if IB is flowing in the circuit, EB junction is forward bias. Okay. And if VC is much larger than this one, that means that your transistor is working in the active region and you get the constant current. IB, you know, IB into beta IB, IC, the current circuit will be flowing. Okay, so and if both this is also reverse bias and EB junction also reverse bias, that means you have removed the battery, you make the IB 0, you make the voltage applicable at the base is negative, then it is everything is reverse bias and you are working in the cutoff region. Okay, now if you see this curve has a very high current gain. Current gain is very high in the circuit. Current gain beta IC upon IB, okay, close to 500. Okay, question varies. Sometimes it will give you 9800, 200, but with maximum it can go 500. Output resistance of this curve is not equal to common base, but still is very high. Output resistance say order of 50 kilo ohm. That was 500 kilo ohm, you say 50 or 40 kilo ohm. But this is most used biasing because here you are getting current gain also, you are getting resistance is high. That means the voltage gain is high compared to voltage gain is very high. Voltage gain is very high in the circuit common emitter configuration. Power gain is very high. We'll discuss this thing later. Power gain also high, voltage gain is also very high in this common emitter configuration. That's why this is the most preferred configuration, and all the problems will make this one. Okay. Now common collector is not that much important. Okay, but let us use that one also. That is not be coming in exam. Common collector configuration. Okay, but just we can draw that one also. Put adding common collector configuration. Common collector configuration. So again, you have to write the equation, fundamental equations. Fundamental equation says IC equal to alpha E plus ICBO. Okay, IB equals to, what is IB equal to? 1 minus alpha E minus ICBO, and what is IE equal to IC plus IB is a fundamental equations. Now you have to change this equation because now if you make common collector, so base remains here, collector goes down. This collector, this is your ammeter, and this is your base. Okay. Now input current is IB. Okay. Output current is your IE. And this is grounded. You're applying voltage here. So you apply, say this is VCC, applying here. Okay. So now input voltage is NPN. Okay. NPN. Okay. So direction is like this. And you are applying measuring voltage here. So this battery will be again, so this is applying to base, so this is VBB, and you're applying here at ammeter, so you can see this is VEE. The battery is VEE. Okay. So BC will be again your output voltage, and here BCB will be your input voltage. Now I want to modify this equation a little bit. How can I modify this equation? So IE, I want to bring here IE. Okay. So what should I do? Tell me. I want to bring IE here. So this is IC. Okay. So what I can do, I can use this equation IB. Okay, 1 minus alpha IE. I can write as a IC plus IB minus ICBO. Okay. Sorry. IE. No? So just give me 1 minute. IE minus IB. So IE minus IB is equal to IC, and IC is equal to alpha IE plus ICBO. Okay. And later you can bring this alpha E here. So I will become 1 minus alpha, and this equation IB will come here. So IB plus ICBO, okay, and IE will become IB upon 1 minus alpha plus ICBO upon 1 minus alpha, okay, and IE 1 by alpha is gamma IB, okay, plus ICBO upon 1 minus alpha. You can say this is again ICO only, na? ICO was same also. ICO common emitter configuration. So here current remains the same. Common emitter configuration. Current reverse current is same. ICO. Where gamma is what? Gamma is your basically what is gamma? You want to derive gamma. Gamma is basically I minus ICO upon IB. This is the exact thing. And if you ICO with negative 0, so your this is current gain IE upon IB. But this is a very high current gain also. IE plus IB. This is also very high current gain. This configuration is very high current gain. Okay, much almost equal to your common configuration because I is almost equal to IC. Okay. Now input output current characteristics actually we don't require for this one. Okay. If you want to draw, you can draw, but we don't require. So input will be what? Now tell me, what is the input current? Input current still remains the IB, the input current, and you have this VCB. Okay. So tell me, input will be what? Input will be what? Input characteristic means IB versus VCB keeping what constant? VCE. I have kept the VC constant. Okay. Now, if I am increasing my VCB, IB will increase or decrease? Tell me, if I'm increasing VCB, what will become? If I'm increasing my VCB, my IB will increase or decrease? Ujjwal, Rajveer?
सर इंक्रीज
अरे यार फिर ये तो क्या मतलब है इतना 2 घंटे से मैं तुमको बता रहा हूँ VCB बढ़ेगा तो क्या होगा if VCB बढ़ेगा तो बेस कितना बेस भी घटेगा घटेगा बढ़ेगा
सर घट जाएगा
घट जाएगा तो आई तो घटने से क्या होगा रिकॉम्बिनेशन कम होगा ओके
यस सर
और रिकॉम्बिनेशन कम होगा तो क्या होगा IB कम होगा
यस सर
IB कम होगा तो this is your this curve will come like this if VCB increasing you are keeping what keeping VC constant for this curve say this is VC 5 volt and I'm plotting this VCB so this will come like this okay now if I further increase VCE so VC increasing VCB means if you increase the VCE again what will happen if IB go further down say this is for 5 volt if I put VCE 10 volt so your IB go further down okay so this is the curve because increasing VCB also reduces the IB increasing the VCE also increasing the VCB because VCE is equal to VCB plus VB that will do same thing now you have to if you want to get same current okay same current then you have to apply more input more this one okay more value what is it VBC yes input current is VCB okay so I'm not discussing this further if some mistake is there I will discuss tomorrow but this common collector configuration is not required for us okay so this is your configuration finished now we will come to our main job okay so how to deal the problems in the exam and what are the problems come in the exams that we'll discuss how much time is remaining Okay, so let us stop here now, because there's too much happening. You want to get. So tomorrow, I will put the comparison data, and I'll finish here. Okay. So now you have a CB junctions, common base. You have a common uh, emitter configuration, and you have a common collector configuration. What are the difference in these? Okay, characteristics. Okay, characteristics. So characteristics means if you want to get the voltage gain, AV, voltage gain, AV, okay. You want current gain, power gain. You want current gain, AC. You want power gain, that is AP, or what should I write? AP here, AP, and then you want input resistance. This table you have to remember. Input resistance, you want output resistance. Okay, and then last is your leakage current. And then you have finally you have applications. Okay. So if you talk about the voltage gain is highest in which configuration? Voltage CE. Okay. So a voltage gain value, say here is medium, here medium. Now your values can change. Okay, this here high is around 400. This values nothing to just comparison you want, which is higher, which is less. Okay, and voltage gain in here, that is less than unity, very less voltage gain is there. That is not required. That's why we didn't discuss this one. Okay, and the next is current gain. Current gain again is high. Here is current gain is how much? Low, less than unity. Okay, less than 1. Say less than unity, because it's IC by IC upon what is the current gain here? IC by IE. Input current is IE. That is say less than 1. Say 0.95, 0.9, 0.8. And here current gain is very high. Current gain is because current input current is IB, IC by IB, and this value is okay. Roughly, I am taking 100, but it's not 100. We'll go 500. Some books give you 500, but we cannot compare. And here, same thing. Input current is IB, output current is IE, so it's also high, around 100. Okay. This just for reference. And power gain values you can take 150, 40, 100. Okay, 150 power gain here is 150. Here 4,000, 40,000, 40,000. Okay, high, and here low. Power gain is value is given 100. Here value is 100. So that's why this is preferred. Here voltage gain is here. Voltage gain is high. Okay, current gain is high. Power gain is high. That's why it's important. Okay, input resistance. Input resistance only high is here. So input resistance is very high. Input resistance all have less. Okay, this is 25 ohm. Low. This is a medium. This 25 ohm. This is a low. Here is a medium, around 1 kilo ohm. Okay, and other side you can put the values low 400, very high 1 mega ohm. Here input resistance is very high, 1 mega ohm, high 1 mega ohm. We'll discuss this common collector sometimes later at the end of the syllabus, at the end of the transistor. And output resistance is high. Okay, output resistance is high here. How much? I told you 500 kilo ohm. And here around 40 kilo ohm. This is the medium. Here is the high. And last here low, 400 ohm. Here also low, 400 ohm. Here is low, 400 ohms. Okay. Leakage current is very small. Here is very small, very large. This is only disadvantage. Very large. This is a disadvantage of this common emitter configuration. Here also very large, and this we have to deal in biasing. And next is your applications. This is used for high frequency applications. For high frequency, this configuration used for high frequency applications. This is used for audio frequency application. High frequency, audio frequency, and the last one is for this configuration is used for impedance matching. This point only you have to remember. Okay. Sometime the objective paper they ask this type of questions. Okay. So here you have this is high. Okay. Remaining these three things are high here. And this you remember, this is for impedance matching. So ये question पूछे आते हैं. So I'll stop here and we'll meet tomorrow. We'll discuss how to use this. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.